So one thing that gets glossed over a lot, I found in organic chemistry courses, is the effect of solvent. And we gloss over it partly just for practicality, partly because it's just a lot of information to take into account. The reality is organic chemistry is very dirty and you end up with a lot of side products. But the one I want to talk about in this video is Sn1 versus Sn2. Sn1 mechanism, as you should recall, is when our leaving group, in this case chlorine on our 2-chloropentane, pops off and we form a carbocation, and then the next step, our nucleophile, in this case cyanide, attacks it. And in Sn2 mechanism, this is a concerted mechanism. So we have Cl leaving as the Cn is pushing it out. How do we select for which mechanism we want? And you may be asking yourself, well, why do I care? Well, I care because let's say I actually had a dimethyl. Well, if I go through an Sn1 mechanism, what's most likely going to happen is that we're going to get a methyl shift. And when we get this methyl shift, we're going to move the cyanide not to the second, adding it to the second, but we're going to add it to the third, and we're going to get a methyl group on the second carbon. So how do we select for them? Well, there's two key factors when picking a solvent. The first is what's called the dielectric constant. So the dielectric constant of the solvent basically says how well does it stabilize charges or screen charges. So if we have a very high dielectric constant, we're actually going to stabilize the carbocation, because while you're going to get a big positive charge, the solvent's going to have polar functionalities of it that are going to basically be attracted to it, and they're going to want to form that positive charge because it's something for them to point at and stick to. So something with a high K dielectric, these are something like water, acetic acid. They do a very good job of stabilizing your carbocation. Something like tetrahydrofuran, or what's the other one I got written down here? It seems to be the only one I got written down here. Look through tables of dielectric constant. Something with a small dielectric constant doesn't really stabilize the charges. The second is whether or not it's a protic or aprotic solvent. And this really doesn't affect the carbocation as much as it affects the nucleophile. A protic solvent, something like water or acetic acid, will actually, the H plus will attach to your nucleophile. Because typically when we look at a nucleophile, it's a Lewis base. So if there's H plus around, it's going to react with it. So what the protic solvents do is they occupy the nucleophile. They're not really quite ready to settle down and commit with something that's got a positive charge. So if we used a protic solvent here, we'd actually have less cyanide, and we'd give the Sn1 mechanism more time to do it. So yeah, more time to do it. Whereas if we had an aprotic solvent, the aprotic solvent is not going to protonate our cyanide, and because of that, the cyanide's ready to go and it wants to react, and so it's more likely to participate in Sn2 because it's not occupied with the protons in the solvent. So when it comes to looking at your reactions, if you have a reaction and for whatever reason you're really worried about it going through an Sn1 mechanism, switch to a solvent with a low dielectric constant that is aprotic, meaning it doesn't have free protons, something like tetrahydrofuran. The reason you're going to do this, the low K dielectric constant, is not going to stabilize the carbocation, and the lack of protons from the solvent means that the nucleophile is ready to go. So you're going to promote the Sn2 mechanism. If you have a reaction and you don't care, or for whatever reason you want to promote the Sn1 because you want to get rearrangements, the ideal solvent here is something with a high K dielectric constant, something with a big dielectric constant to stabilize that carbocation, and something with a lot of good protons in it, a very protic solvent, that will occupy your nucleophile so there is time for that carbocation to